So we've just seen how we developed kinetic energy relationships using the definition of work and one of our motion equations and coming up with the kinetic energy equaling 1/2 mv squared. Now let's look at potential energy. By definition then, potential energy is the energy that an object has as a result of its position in space, the surface of the Earth, called gravitational potential energy. Okay, so the further we are from the surface of the Earth, the more gravitational potential energy we have. The closer that we are, or the closer that we are to a surface, will change the potential energy. Okay, so we need to keep that in mind. So again, we're going to go back to our definition of force, and we said that force was equal to ma. Force is equal to mass times acceleration. Well, in this case, since we're in the vertical axis, we're going to define the acceleration as the acceleration of gravity, or g. So now we have force is equal to mg. So we're going to kind of do the same thing. Now we're going to use the positioning aspect here by using the change in position on the y-axis. So we're going to say that delta y, the change in y, is equal to y initial minus y final. Okay, so now we're going to take those two relationships and we're going to put them together to come up with a definition for potential energy and a relationship. So now we're going to say that the work, not the work net this time, but the work due to the gravitational acceleration, g, is equal to mg times the change in y. Where before we had ma times the change in x, now we're going to have mg times the change in y. And since delta y is equal to y initial minus y final, we can expand that then to be mg y initial minus mg y final. Okay, and again, using the definition three bars, potential energy then is defined as mgy. Okay, and now substituting then back, we can say that the work due to the gravitational acceleration is equal to potential energy initial minus potential energy final. We can see from the diagram here that in every case, the potential energy is relative. If we take the book and just lift it up off of the desktop, we've got potential energy based on the distance between the book and the desktop. If we move the book out away from the desktop over the floor, we have increased its potential energy. Then one more step, if we take the book and hang it out the window, now we've got all this distance, delta y, that is increasing the potential energy. So for potential energy, the work done on any object by the force of gravity is equal to the object's initial potential energy minus its final potential energy. The units of gravitational potential energy are the same as before. Nothing has changed. Joules, ergs, foot-pounds, Newton meters, kilogram meters squared per second squared, they're all the same. It's just related now to the y-axis. Potential energy then, like work and kinetic energy, is a scalar quantity. So let's look at an example on how we can use the potential energy relationship to help us determine values of interest, in this case, the potential energy. A 60 kilogram skier is at the top of a slope. At the initial point A, the skier is 10 meters vertically above point B. So point A is up here, point B is down at the bottom of the slope. The first question they have is setting the zero level for gravitational potential energy at B, the bottom of the slope, find the gravitational potential energy of the skier at A and at B. Then find the difference in potential energy between the 2 points. So again, we gather what we know. The mass of the skier, 60 kilograms. Again, that's not the weight of the skier, that's the mass of the skier. The initial point, Y, initial is 10 meters. Okay, that's at the top of the slope. And the final point, 0 meters at the bottom of the slope. So find A, setting the zero level for gravitational potential energy at B, find the gravitational potential energy of the skier at A and B, and find the difference in potential energy between the two potentials. So let's start with the definition. Now potential energy is equal to mgy initial. Okay, so this is at the top of the slope. 60 kilogram skier, 9.8 meters per second squared. We're going to choose that value for our acceleration of gravity, and 10 meters of height. So multiply those together. We have an initial potential energy at the top of the slope of 5,888 joules or Newton meters for the energy potential at the top. Because the potential energy at the bottom, final, is 0, we don't have to do any calculations. We know that it's 0. Why? Well, because there's no energy left once the skier gets to the bottom, and we know that Y final is 0. So we end up then just taking the difference between potential energy initial, potential energy final. We get a 5,880 joules of potential energy. Okay, so now on our next segment, we're going to take a look at how do we determine what forces are conserved and what forces are not conserved as we start doing things with these objects in moving them either in space or moving them along the x-axis.